So in our next section, we're going to start to talk about the new standard for spanning tree that is known as the Rapid Spanning Tree Protocol, or RSTP, where the original version was defined by 802.1D as in David. The new standard is defined by 802.1W, which is the rapid variation of this. The key is that it takes some of the enhancements that Cisco added for their per VLAN spanning tree, like the same behavior as what PortFast does or what uplink fast does, but it puts it into a new standardized protocol so anybody can run it, whoever wants to run the implementation. And the result is that we actually get faster convergence than the legacy network, because the switches go through basically a handshaking or a negotiation process when they first build the network. So they first agree on what the topology is, and they can do this very quickly. The end result is that if a switch fails or if a link fails, you're able to rebuild the network very quickly around it, or to rapidly converge. Now, the logic of the spanning tree is the same as the regular spanning tree algorithm, or what we sometimes call the STA versus the STP. So it's building the same type of tree, where the overall logic is going to be that we have a root of the topology, or a root of the tree, and everyone is going to be building their topology based on the root as the reference point, where these other switches downstream are going to have a root port that forwards upstream, and then they're going to have other downstream facing interfaces that go towards like the end hosts, or that go to other leaf nodes of the topology. So same type of logic, we're going to only build one physical path that goes up to the root. But behind the scenes, we use a different algorithm to negotiate this, but at the same time, it's backwards compatible with the old one. So there's cases that you can have your common spanning tree talking to per VLAN spanning tree and talking to the new rapid spanning tree format at the same time. So it eases the migration of the original protocol to the new one. One of the key enhancements we'll see is that it simplifies the port states. And the rapid convergence is going to be based on a synchronization, or essentially a handshaking process between the bridges. So when we talked about the original algorithm with 802.1D, it uses 5 different port states, where we have a disabled link, which would be like administratively down. We have a blocking link, which cannot send traffic out because that's the looped portion of the topology. Then we have the links that would be in the listening, learning, or forwarding state, where again, listening and learning, this is when we're trying to build the MAC address table and learn where are the hosts located before we actually insert ourselves into the topology. And then forwarding, this is finally when we're sending the traffic. The blocking is where we are preventing the loops. So the rapid spanning tree algorithm takes this and it simplifies it into kind of a combination of these roles, where the first we have is discarding. Simply means that we're dropping frames. So whether it's discarding because the physical link is down, or it's discarding because it's in the equivalent of the blocking state, this is when we're not sending traffic out the interface. The next one is when we're learning the topology. We're still dropping frames, but we're building the MAC address table. This is the combination of the listening and learning phases. So they're collapsed into just one, where we're trying to learn the topology. Then the third is when we're forwarding traffic. So we're taking these 5 and then combining them just to the 3. Either we're dropping traffic, so we're discarding, we're learning the network, or we're forwarding the traffic. We also have a difference in the port role versus the port state, where in the regular spanning tree we have the disabled, blocking, listening, and learning, and forwarding stages. In rapid spanning tree we have the port states, which are discarding, learning, and forwarding, and then we have these different port roles. Where the port roles, we have the root port and the designated port. These are the same as before. Where the root port is pointing upstream towards the root bridge, the designated port is pointing downstream away from the root. But then we have the introduction of this alternate port state. This is what Cisco was using for the uplink fast feature, basically saying that it's my backup port in order to get upstream towards the root bridge. So it's an alternate, but it's a less desirable path to the root. So it has maybe a higher cost value, or someone out that link has a higher bridge ID, so it's going to be the less preferred path. But the key is that this is going to allow us to do the equivalent of uplink fast, which means that if the root port goes down, we can immediately start forwarding over to this alternate port. This is going to be operating in the discarding state, which means you're not sending traffic out, you're not receiving traffic in. It's essentially the equivalent of a blocking port. But then we have a completely new definition, which is a backup port. This is an alternate designated port, where it's very rare that you would actually run into this role, but it's when you have two downstream facing interfaces that go to the same segment. So it would be as if you were connected to like a hub downstream and you're on the same physical segment. Most of the time you wouldn't see this because this is a downstream facing backup port where it would have to look something like this. You have switch 1 that in this direction upstream is the root. Then downstream is normally your designated port. But if I were to have some sort of other layer 2 device, like a shared hub here, and then I connect to switch 2, but I also have an alternate link that faces down to that segment, this is what the backup port would be. So it's not as common as you would see this because normally the bridges are connected in point-to-point fashions, where there's a direct Ethernet link between them and it's a full duplex link. Yes?
Wouldn't that be a block port?
It runs in the blocking state, it runs in the discarding state, but it's your alternate downstream facing interface, where or I shouldn't say alternate because alternate is actually one of the port roles. This is a backup upstream port. This one here is a backup downstream port. So I'm not really 100% sure what case you would have this in. You would have to be connected to some sort of shared segment that you're trying to run a spanning tree over. But normally you don't have this because the switches run in a point-to-point fashion where they're directly connected to each other. Yes?
Line, right? It's a whole row decoupled from state. What does that mean?
It basically means that what the port is actually doing, like if the port is discarding or learning or forwarding, it's unrelated to what the role of the port is. So this is how this is the port in respect to what the topology looks like, where the root port faces up, the designated port faces down, the alternate port also faces up, but it's a backup. The backup port faces down. Then what the ports are actually doing, whether they're forwarding the traffic or whether they are discarding, it's a separate calculation internally, so they're not directly related to each other. We also have what is known as an edge port. An edge port is basically the equivalent of a port-fast enabled port for per VLAN spanning tree, where the idea of a port-fast port is that when you connect it to the LAN segment, you don't want to have to wait for the listening and learning phases. So you go from blocking immediately to forwarding, or you go from disabled immediately to forwarding. The edge port in rapid spanning tree basically does the same thing, but it's technically not a port-fast port. What makes it even more confusing is that to turn a port into an edge port, the command that Cisco uses is the spanning tree port-fast command. So the idea behind this is that when you migrate from per VLAN spanning tree to rapid spanning tree, you want what used to be your port-fast ports to now become edge ports. So it uses the same command in order to ease in the migration process. So it ends up to be the same result, but behind the scenes they work a little bit differently if it's an edge port versus a port-fast port.
Will the default also work in rapid spanning tree?
It will. It will. The key behind this is that the edge port is going to stay as an edge port as long as it's not receiving BPDUs. So just like with the newer functionality of the Cisco switches, if you use that default portfast feature, it says all of my access ports are going to be in portfast state. But as soon as I hear someone running spanning tree, I'm going to transition it to a normal port. That's where this is going to come in. That you can essentially configure every link that is an access port as edge. But if someone plugs a switch into the network, you want to make sure that you can automatically react to that. And it's based on the reception of the spanning tree advertisements, or the BPDUs. So it's the same type of operation as the regular spanning tree, where you generate that topology change notification, and then you're going to go into the normal negotiation of the topology, including that interface. Now the different ports are going to fall into two different categories of link types, which are considered point-to-point links and shared links. A point-to-point link is basically a full duplex interface. So it would be a connection directly between two switches. Where a shared interface, this is going to be for backwards compatibility of anything that's running in half duplex mode. So if for some reason you still had a hub in the network, then you could connect the spanning tree segment, or the spanning tree, to that portion of the network, but that would be considered a shared segment. And the key difference between the two of them is that the handshaking process, or what we call the sync or the synchronization process, it's only going to happen on point-to-point ports. So if you connect to a hub or some legacy portion of the network, you cannot run rapid convergence on that segment. You fall back to the original spanning tree algorithm, which is you wait for the listening delay, you wait for the learning delay, and then ultimately you can go into to forwarding. So the next thing then would be to figure out what's the difference in this synchronization process, where in the regular legacy spanning tree, only the root bridge is going to be advertising the BPDUs. So when the switches originally joined the network, they're sending BPDUs everywhere to exchange what is their bridge ID and figure out who gets elected. Once the root bridge is elected, the BPDUs are going to start at the top of the tree, at the root, and they're going to flow downstream out everyone's designated ports. So the BPDU is coming from the root bridge out the designated port. It is received in the root port of the downstream switch, and then it continues to get forwarded out the designated ports. But the problem with this legacy algorithm is that there's no bidirectional communication between the upstream switch and the downstream switch. And this is why it takes so long to converge. Spanning tree, the original specification, is kind of like a connectionless protocol, that you're just sending the information out, but you're not trying to solicit a response back in. So when I send you a BPDU, I really have no guarantee that you actually got it. It's just a multicast packet that goes down from the top of the tree towards to the edge, to the leaf nodes. So this is mainly what the synchronization process is trying to solve. That if the bridges have an active communication, kind of like how a routing protocol adjacency works in like EHRP or OSPF, they're going to go through this negotiation process to figure out, first off, who is the root bridge. So we try to elect a root bridge just like we do in the previous version of spanning tree. Once we do that, we want to make sure that the entire network agrees where the root is located and what are our root ports. So what are the interfaces that are facing upstream towards the root bridge. So when the bridge first joins the network, it's going to figure out who is the root bridge and then what is my root port. Every other interface on the device is then going to go into the discarding state. So in this case, where we have the root bridge and then switch 1 joins the network, we have the normal BPDU exchange between them, which is advertising inside of their bridge ID. They're going to be advertising the priority value. They're going to be advertising the system ID extension, which is basically the VLAN number, and then what is the MAC address. So the switches exchange these based on whoever has the lowest priority, or if there is a tie, whoever has the lowest MAC address, they're going to be elected the root bridge. At this point, switch 1 says that the root is located here, so this is going to be my root port. At this point, any of my other interfaces, they now go into the discarding state, and I initiate the synchronization process again downstream. where the idea is that these switches are going to quickly do this handshake process back and forth, agree on what the root port values are, and continue to calculate this away from the root, and eventually, within a very short amount of time, be able to agree on the entire topology. So once we first figure out the root port, then everything else is going to go into the discarding state. The other key point here that's a difference between the original specification and the new one is that this only counts for non-edge ports. Because an edge port, we're assuming, goes to an end host, like your laptop or your printer or something like that, where it's not part of the spanning tree topology. So we can just immediately move that into the forwarding state. And then for any of the other interfaces, those will be in discarding until we can actually ask downstream with the synchronization process, do you agree on who the root bridge is? Do you agree that I'm upstream of you? Then if that agreement occurs, then it can continue to happen downstream. So specifically, this synchronization happens with what we call a proposal. So we agree that the root port is facing upstream. Out all of the downstream ports, we send the proposal, basically saying that the root bridge is upstream of me. Do you agree on this? And during that process, we're exchanging the normal bridge ID options, like the priority, the path cost end-to-end for the root bridge. It's the same type of logic as before. But the downstream device is then going to look at this and then tell the upstream device, either I don't have a better path to the root, and you were correct to begin with, or I do have a better path to the root, so you need to now put your other ports into discarding and resynchronize those. So the idea is that it's a very fast handshaking process that eventually is going to sort the topology out. And in general, it's going to happen in less than 1 second for the entire network. Now, once the switches agree that I have this interface facing upstream towards the root and I have another interface facing downstream, which is designated, then the designated ports can become unblocked and start to forward traffic. So the transition period between discarding and forwarding is very, very fast. It's just the amount of time that it takes them to do the synchronization and then to agree on who is going to be the root port, who is going to be the designated port. So the key is that if the downstream device agrees, they're going to say that the port I received your proposal in, that now becomes my root port, because that's facing upstream towards the root bridge. This is then going to continue again downstream, where you block all the non-edge ports, you continue to send the synchronization process. What this is going to do is to make sure that while the network is in the process of converging, you don't cause a loop. And the term for this is what we consider to be a transient loop, or basically a temporary loop in the network, where certain protocols like OSPF routing can cause what's known as a transient loop, that while the network is exchanging the OSPF database and trying to synchronize, two routers could have differing information. And I would say to get to A, I'm supposed to go that way, where another router says to get to A, I'm supposed to go the other way. So by temporarily disabling the interfaces, this is what we're preventing with this, is that there should not be a temporary loop, or there shouldn't be a transient loop, because they have to agree to the synchronization process before you're actually allowed to send the traffic out. Now, as I mentioned with the original spanning tree, only the root bridge is the one that's generating the BPDUs. So the amount of time that it takes to notice that there's a change in the topology is going to be the difference between how often am I sending hellos and what is the maximum age timer, or how long should I wait before declaring the root bridge information is no longer valid or stale. So they come down for the root bridge, everyone else is going to forward them downstream. In rapid spanning tree protocol, every link on every bridge is going to be sending BPDUs outbound to the other switches and then receiving them inbound. And this is going to be using a 2-second interval by default. The key difference is that if we miss 3 hellos in a row, so in about 6 seconds, we will start reconverging, as opposed to the 20-second max age timer. What this is going to prevent against is a software failure. That if it looks like the link between you and me is still physically up at layer 1, but for some reason you're not responding to the BPDUs, like if the spanning tree process crashes, then I'm going to know in 6 seconds as opposed to the 20 seconds, which is the default for the other algorithm. The other change here is that the maximum age is still going to be used, but we're basically going to use this as a hop count in the network, where every bridge is going to be sending its own BPDUs, so both upstream on the root ports and downstream on the designated ports, and the age value is going to be incremented for every hop that we move along the network. We'll see also that for any port that goes to the legacy portion of the network, like if I detect that someone is running the common spanning tree, on that interface I then need to use the maximum age to make sure that they can converge if there's a change in the topology. So you're basically allowed to run both algorithms at the same time. The switch is going to detect, is this portion going to a rapid spanning tree switch or is it going to a legacy common spanning tree switch? The other key point here is that when a physical link goes down, the switch is automatically going to start to reconverge. Where in the previous case, when we were looking at the links between switch 4 and switch 2, and then switch 4 and switch 3, we had the situation where switch 4 was saying this was my root port to get up to switch 1, which was the root. When this link directly fails, so if there's a physical link cut between them where the interface goes bad and the link status, which is the layer 1, goes down, it doesn't make sense that the switch should then have to wait another 30 seconds before it begins to forward traffic. So in the case of rapid spanning tree, if you have this direct failure of the physical link, it's automatically going to restart the synchronization process. That switch 4 knows that there's a change in the topology. This is no longer my root port. What became what previously was either my designated port or what was in the discarding state, like a blocking interface, I'm just going to ask them with the synchronization, or again what's sometimes called the proposal, what's the situation for you in terms of the rest of the network. So when I send the proposal to them, I'm saying to them, I'm the root bridge. Switch 3 may reply back and say, no, in reality, switch 1 is the root. Then switch 4 accepts this and can immediately transition its interface into to the forwarding state.
So it's learning and forwarding. It goes from that, I don't know, like 0/19, it changes from blocking to learning and then forwarding.
And let me see, I should have a... I don't have it on the slides here, but let me go back to the previous ones. So these states here, discarding, learning, and forwarding, this one is only needed if you are not a point-to-point link and you are not running rapid spanning tree protocol. So the switch is going to know, are you running the original version of the spanning tree algorithm or are you running the new one? Because it supports basically both frame formats, the original format and the new one.
Right, but what's that state when it's asking for the proposal and receiving? What do you call that state?
You're in discarding.
Oh,
so
it's discarding?
yeah, so it's dropping the packets, but as soon as you agree on the synchronization, you move immediately to forwarding.
Okay.
So the key is that learning is only used if you're attached to the legacy portion of the network. If the network is running only rapid spanning tree, you're going to go right from discarding to forwarding all the time. But it's the only time that you need for that transition is how long does it take to do the handshake, and it's just a couple milliseconds to do
Although
it.
you're in discarding, you're still receiving those proposals.
Correct. Yeah, so it's dropping frames in terms of like your actual end user traffic.
Gotcha.
But the key is that you're always still sending and receiving BPDUs on your interfaces. And that's one of the key differences, that again with the, the normal spanning tree protocol, the the BPDUs are only generated by the root. Where with rapid spanning tree, it's generated by every bridge on every interface. So I know that if your link goes down or I miss 3 hellos from you, I can immediately start to reconverge. So this is what we're using to do that synchronization process is part of the BPDUs. Now, as I mentioned, one of the features of this that's automatically on is that if your directly connected root port goes down, instead of doing a new synchronization, if you were to have an alternate port, you can immediately transition to that. And that's kind of like the functionality of uplink fast. That I know I have one connection to the root bridge, I have an alternate link that is a worse cost to get there, but it's still a valid path. So if my directly connected root port goes down, I'm immediately going to transition that alternate port into forwarding and then send a new synchronization downstream to make sure that I haven't caused a loop by transitioning my alternate port now into to the forwarding state. If for some reason I don't find any other alternate ports, which would be the case like that we had, the case we have here, where in the case of switch 4, it has an alternate port and it has its root port. When the root port goes down, it knows that this one is pre-calculated to be a path to the root. So this alternate port immediately gets promoted to the root port and we're able to start forwarding the traffic. But if for some reason I don't have this connection, so let's say that switch 4 only has one connection upstream, but it has multiple connections downstream. If this root port is lost, what it's going to do is then elect itself as the new root bridge and tell everyone else downstream in the topology that I don't have any other paths up to the root, so we need to resynchronize this portion of the network. So essentially, it's just going to restart the synchronization process, which means that maybe we could find an alternate path, or maybe the root bridge is down completely, and then our promotion to the root bridge is actually a valid case.
Well, if there was an alternate path, that switch should have known it by blocking.
But the key is that the alternate port faces upstream.
Right.
You could potentially have other downstream paths to reach the root bridge, but you wouldn't know that until you lose your root port and you lose your alternate ports, because it would mean that other portions of the topology would have to resynchronize to agree with you. Because the key is that the alternate port is facing upstream.
Right.
You can't switch from your root port to a downstream facing interface. You can only switch from your root port to an upstream facing interface.
What I'm thinking, you could not have a third port that's connected, a path to the root bridge outside of these 2 ports, the alternate and, or could you?
No, you couldn't.
Okay.
Correct, right. The only issue with this is that there can be some certain strange designs with rapid spanning tree where it's considered to be a non-deterministic protocol, where you can't really predict what is the worst case convergence time that you're going to result in. One of the design limitations of this is that if there's tons of connections between the switches, or what we would consider a highly meshed topology, lots of interconnections between the switches, the convergence could be slow. Also for large topologies, it could be slow. There's some design cases that they've come up with that rapid spanning tree never converges in certain topologies. Then you basically have to break loops in the network, let it sort itself out, and then you can rebuild the network again. But in most case scenarios, when you compare the legacy spanning tree to this, it's going to be a better design choice to use rapid spanning tree as opposed to the original one. So the overall fix for this would be just to keep your layer 2 spanning tree topology small. Because we'll see anytime that we introduce layer 3 routing, we're already breaking up the layer 2 network. So the spanning tree is only constrained to an individual VLAN, or the layer 2 trunk links that are going between the switches. Anytime layer 3 routing gets in there, it's going to terminate the spanning tree domain. So on this side of the network, I have one spanning tree, and on the other side of the network, I have a different one.
And that's preferred or no?
It depends on the application, is what the problem is. If the application needs direct layer 2 attachment, then you really don't have an option. You're going to have to run spanning tree. But if the application is something like just a TCP application, like web browsing or something like that, then probably layer 3 routing is a little bit better design choice than the direct layer 2 attachments. Another way to get the network to converge a little bit faster is to try to rely on the physical layer failure and not necessarily on the hellos, where again the hellos are going to be generated every 2 seconds, and if you don't hear a response within 6 seconds, it means that you start to reconverge. But physical link failures generally can be detected a lot faster than this. Like in the case of most fiber interfaces, it's somewhere in the order of like 10 milliseconds or less that the interface driver actually knows that the physical signal is not there. And rapid spanning tree is automatically going to detect this, that the physical link goes down. Now, we still need to tell the rest of the network if something is changed in the topology, which originally was generated by our topology change notification, or the TCN. This is going to be generated when the link moves to forwarding state. And the idea behind this is that we're trying to, again, flush out the MAC address tables. So anytime there's a change in the topology, the switches need to make sure that their layer 2 forwarding tables are correct and that I don't have the MAC address pointing out the wrong interface. The way that you can fix this, though, is just like in Cisco's enhancements for spanning tree, is you want to try to use edge ports as much as possible. Because these ports, they don't generate those topology change notifications, because we know that they're not really part of the tree. They're just the leaf nodes or the edge of the network.
By that you mean access layer ports?
The access layer ports, right. So if the port is not going to another switch, it should be an edge port. Only the inter-switch links really are the ones that need to participate in the actual calculation of the topology. There's a second enhancement that also goes along with this that is defined in 802.1s. They run hand in hand, though, where this one is the multiple spanning tree protocol specification. The other one, 802.1w for rapid spanning tree, both of these are going to run together. Where originally Cisco came up with this as multiple instance spanning tree protocol, where the idea is that instead of having one instance of spanning tree for every single VLAN, we can just specify how many we want. So if I have 1,000 VLANs, instead of running 1,000 instances, I could say maybe I only want 10 instances where I'm going to group each of the instances together with 100 VLANs. So you try to look for cases in the network where one VLAN follows the same physical forwarding path, then you group that into the same calculation. So in the end, you end up with the ability to still do layer 2 traffic engineering, which is like to change your path selection, but you don't have as much overhead as running a single instance for every single VLAN. But the key is that when you're running multiple spanning tree protocol, or MST, it automatically uses the rapid spanning tree protocol for that synchronization process. So they run hand in hand.
Yes. When you have an Ethernet port, Ethernet channel line, let's say include 4 ports, one port actually failed for some reason, and you didn't have the core fast edge configured.
Mm-hmm.
Would that create some kind of
It depends where the port is attached. If the port is between 2 switches, so let's say you have these interfaces channeled together between the switches, regardless of whether this is common spanning tree, per VLAN spanning tree, or rapid spanning tree, the actual negotiation, which of the Ether channel, or the standard one, which is the 802.1ad, the goal of these two, and we're going to talk about this in more detail today, the goal of these two protocols is that we hide the details of the topology from the spanning tree process. So a spanning tree isn't running 4 times on the individual links. It runs as one grouping over the logical channel. So if one of the member interfaces of the channel goes down, it doesn't affect a change in spanning tree. The only thing that it would do is it would change the cost, the spanning tree cost of the bundle. So they would need to exchange that new attribute to see if the topology is still correct. But it doesn't necessarily mean that the rest of the links stop forwarding their traffic. So we'll look at that case when we're using channels, and then if one of the links goes down, what's the result in the spanning tree? So again, with this variation, the multiple spanning tree, which is sometimes called the MST or the MSTP, the idea is that we're separating the instances of spanning tree from the VLANs. There are now 2 separate entities that we're going to deal with. And in order to design this, we then need to choose how does the spanning tree relate to the VLAN. And we're going to do this with a manual association. In a multiple spanning tree, we also have what's known as the region. This is designed for very large layer 2 networks, where most of this is going to be outside of our scope. But there's some detailed write-ups that we have on this one as well, understanding multiple spanning tree protocol. And the idea for this is that from a large service provider point of view, we have, there should be a diagram here, what is known as multiple regions of the network, where inside a region, the normal spanning tree process runs here. So there's 3 switches. One of these is going to be the root bridge. They would do their normal calculation inside of this tree. But then when we attach the different regions, the result of this basically looks like this, where you have region 1, region 2, and region 3. So even though these individual regions are made up of multiple physical switches, they behave as if they were all collapsed together into one virtual bridge. So you would have one regional root port that is elected between them, where this may be root, this may be root, and then this ends up to be blocking. It's one of the ways that they came up to try to scale the spanning tree network, where you don't have to have all of the bridges in the network participate in the same topology. So in real designs, I haven't really seen too many applications of this, because when the network gets that large, you usually just use layer 3 routing to solve the problem. But the idea is that for large service provider layer 2 networks, if they're trying to do something like Metro Ethernet end-to-end, they may want to separate the network into these different logical groupings, and then say that between the regions, you're always going to forward the traffic in this direction. But if one of the bridges here fails, I don't need to have to recalculate the entire spanning tree in a different region.
You mean switch 1, 2, 3, or 1, 2, or 3?
They're considered region 1, region 2, region 3.
Oh,
So inside of these regions, there's multiple physical bridges, but when they start to interact with each other, they look like they're single switches. So this is kind of going to be out of our scope, the multi-region implementation. This is for really, really large layer 2 networks. But if you want to get more information on it, there's this write-up on our blog about it, Understanding Multiple Spanning Tree Protocol. So when you compare the original algorithm versus the new one, it's a lot more complicated behind the scenes. But when you actually look at the implementation of it, it's very, very straightforward. Now, there's essentially 2 different ways that you can run this in the Catalyst iOS. We can run multiple spanning tree protocol, or we can run rapid per VLAN spanning tree protocol. This one is a really easy migration change, The only thing you need to do is add one command on the switches, which is the spanning tree mode rapid per VLAN spanning tree. What this means is that you're still running an instance of spanning tree for every VLAN, but you use the new rapid algorithm and that handshaking process as opposed to the previous legacy one. Because when we looked at the output of show spanning tree, even though the switches are running a different instance for the different VLANs, the protocol itself is still the IEEE 802.1d, the original specification, which means you use the hello timer, the max age, the forwarding delay in order to do the convergence process. And then you have the root ports, the designated ports, and then the ports can either be in the blocking state or the forwarding state. So again, even though that by default there's multiple instances of spanning tree, one per VLAN, you're still running that legacy protocol, the 802.1d. When you issue this command, spanning tree mode is rapid per VLAN spanning tree. When we look at the change in the show spanning tree output, we're now running our STP, and the switch is automatically going to know which of the portions of the network connect to the legacy protocol. Where on these interfaces, even though overall we're running rapid spanning tree, it's running backwards compatibility on these ones. So it behaves the same, where it's going to use the hello timer, the max age, and the forwarding delay in order to do the convergence. But for any portions that connect to someone else running rapid spanning tree, then we can run the synchronization process. So it means that you don't have to make the change in your entire network all at once. You can make it slowly and do the migration, and then the network is going to figure out, do you connect to the original portion, or do you connect to the new portion? So let's configure this on all four of them. Again, it's only going to be this one command, that the spanning tree mode is rapid per VLAN spanning tree. When we now look at the result of show spanning tree, it tells us what is the port's role. Is this a designated port? Is this a blocking port? Is this an alternate port? And what is the type? So is it shared, which would be for half duplex, or is it point-to-point? Any of the point-to-point ports we're allowed to run the synchronization on, which is that proposal back and forth between the two of them. You can see the details behind this if, and also let me look at the show VLANs. Let me remove all those ones that I added before, because this is going to be basically too many copies of spanning tree for these switches to run.
Sorry, could you repeat what shared was?
Shared goes to a half duplex segment. Like if it connects to a hub, it would be shared. So let's look at this just for the VLAN 1. If we look at show VLAN on the switches, we basically have just the default. And this is going to be for all of the ports. If we now look at the show spanning tree for VLAN 1, the logic is going to be the same between them, where we have the MAC address, we have the priority value, we have the system ID extension, and we're going to be using whatever the lowest of the priority values is to figure out who is elected the root. So it's the same as before, where on switch 1, if we look at the show run include spanning tree, these changes I made here where I had VLAN 1's priority set to be 0, it still means that this bridge is going to be the root bridge, But the difference is that now we can use that handshaking process between the switches. We can see this specifically if we look at the debug spanning tree synchronization. This shows the handshaking between them. Next, let's look at the show interfaces trunk, where right now on switch 4, this link here, this is shut down. Previously, this was the one that we were using as the root port. And it was configured as the root port because I had changed what the cost value was. So this should be the preferred path because it's going to have the lowest end-to-end cost. This means when this new interface comes up, it's going to cause a change in the topology. Where previously the change in the topology means that we would have a ton of packet loss, because it takes 30 to 50 seconds for the original algorithm to agree on the new process. But now, since we're running rapid spanning tree, we should see that once the link comes up, that the switches go through this proposal process, where it says this one is the root port, this is the alternate port. So it actually converged immediately, but it didn't show debug spanning tree. That one may be just for multiple spanning tree. Let's try events. And also, I'm going to remove any of the other changes I made. Like uplink fast, this is not going to do anything anymore because now we're running in rapid preview on spanning tree. The port fast command is still being used because this is the equivalent of the edge ports for rapid spanning tree. So again, the idea for this is that what used to be a port fast port now becomes an edge port. But the syntax doesn't change, so when you do the migration, it's automatically gonna work. So router 4 is still sending traffic. This is to router 1. Let's now say that the port that we were using to forward, which is this one, I'm going to disable this again. So the convergence there, this is just with all the defaults. The convergence is about 1 second. But the switch should then see, it says it's updating the port roles. The root port went down, so now Fast Ethernet 19 is the new root port. It automatically knew this because this was an alternate port, where again an alternate port faces upstream, which if the connected root port goes down, then we're going to immediately transition to this one.
The designated ports face downstream.
The designated ports face downstream, right. Now, if both of the ports were down, so I don't have any connection right now to the rest of the spanning tree network, it says we became the root bridge. And let's try this. Let's try debug spanning tree. MST proposals. Even though I'm not running multiple spanning tree, I think the output is going to show under this debug. And what I need to actually show here is the timestamps to the millisecond level. Let's say service timestamps for the debug messages. The local time to the millisecond. If we show a spanning tree for VLAN1, right now we have one path upstream. We see these other ones that are 4 and 6. These are point-to-point ports, and these are edge ports. This means that they're basically running in the port-fast state. So if there's a change in their topology, if one of those links goes down or it comes back up, it's not going to cause the rest of the network to have to do any recalculation. If the additional link comes back up now, it said that the link state came up, so the layer 1 status comes up. At 339 milliseconds, we now start to run the rapid spanning tree process. It says faster than at 16 is designated. We're sending the proposal. We're asking the other side of the link, am I supposed to be the root port or are you supposed to be the root port? The other side replied with a superior BPDU. Basically what this is a better cost to the root. So sometimes the BPDUs are considered superior or inferior, where superior BPDUs should be coming in your root port. That's your best cost. Your inferior BPDUs would be coming in your downstream facing interfaces, like your designated ports. So at 339 milliseconds, the transition starts. We get the response at 579 milliseconds afterwards. 16 became the new root, so it only took about 200 milliseconds for it to calculate the topology on the link. And this is without changing any of the other options. You just turn it on, and basically everything is going to happen automatically. It says that 19 now needs to go into the blocking state. Eventually we figure out that this one is alternate. So now if the topology changes again, let's say that the current root port goes down. Before we even get the link down message, rapid spanning tree transitions the other root port automatically. So the key is that all those additional enhancements that Cisco wrote into per VLAN spanning tree, they're now part of the standard. So there's really no reason to run the original spec or Cisco's changes, because if you don't want to change any of the design, the only thing you really need to do is just add this one new command, which is the spanning tree mode rapid per VLAN spanning tree. Some of the newer versions in Catalyst iOS, they'll be running this by default, which is fine because it's still backwards compatible with the original algorithm. And it figures out what portion goes to the new rapid portion of the network, which portion goes to the legacy portion.
Does it require some kind of downtime that when you implement this one to some switches, since there's so many switches, right, it cannot finish them in one shot, right? Would it require maintenance downtime?
It can. You would want to do it during like a maintenance window. But the key is that once they originally synchronize the topology, any new changes, it's going to reconverge really fast. But for ports that go to the original algorithm that's running the 802.1d, you would see this in the show spanning tree output. It says that this is a regular STP portion of the network. Then eventually when it changes over and we look at the show spanning tree, you want to see either point-to-point or point-to-point edge. This port here, 24, says it's shared. It means this is half duplex. It means that on this interface you cannot run the synchronization process. So you would have to go from the discarding state to learning before you go to forwarding. And the result of that is the same as going from listening, learning, and forwarding.
So in the rapid per VLAN spanning tree, it's still obviously per VLAN, correct?
It's per VLAN,
If you wanna
right?
do user assign, you have to go into MST.
Correct, yeah. So this is going to be the main difference between the two of them, that if you still want per VLAN control, the easiest way is just to turn rapid per VLAN spanning tree on, because all the command syntax runs the same. Just behind the scenes, it's using that handshaking process to figure out the topology, right, the proposal. The next one we're going to look at is the multiple spanning tree protocol, where we can define what are the different instances. Then here we'll have two copies of the topology, instance 1 and instance 2, where we define that VLANs 10, 20, and 30 fall under this topology, and VLANs 40, 50, and 60 fall under this one. So you don't have to run the calculation for every single VLAN. You get to choose which of them are grouped together in the different instances.
So before we move on, if you're running RSTP, essentially you have to run RST and MST in concert with each other. And then if you're running Cisco's version, RPVST, that's essentially rapid spanning tree with PVST.
Correct. Yeah. So if you say there's three different modes that the switch supports. If you say spanning tree mode PVST, this is the default one. So it runs the legacy algorithm, but it runs it on a per VLAN basis. This one runs the new algorithm, still on a per VLAN basis. This one runs the new algorithm and runs the manual definitions of the instances. Where they're two different specifications, but they're typically used hand in hand. Where MST is defined by 802.1s. Inside this, it says reference 802.1w to see how the actual process of building the topology works. The problem is that this one, we'll see, it's going to take a little bit more design to migrate to this one, the MST. But the problem is that if you have non-Cisco switches, they're not going to support this version, the rapid per VLAN spanning tree. They would only support the MST, the multiple one.